We're now starting shallow foundations, and before we dive into things, I want to make a few notes that need to be made about the way this course is organized. Or some of you are probably looking at each other and thinking not organized. Okay. When I first started teaching the slideshow and with the slide presentations, my goal was to have one slide presentation and one class session. And that over the years kind of got raggedy around the edges. Sometimes my slides would run 2 or 3 class sessions. Sometimes you would quit one, start another one. Well, for this particular semester, what I have done is the slides are organized around, for those taking the course, homework sets. So therefore, the first slide set does not have a homework. It's just an introduction, which is what we did last time. The second one, this one, is for the first homework set, and it covers, is one slide set for the whole thing. However, I know that I am planning on splitting this up into 2 lectures, and YouTube keeps telling me that people don't stick around for your videos very long. So, with that in mind, what I'm going to do is this is going to be one slide set, but we're going to split it up into 2 separate lectures. And this is the first one. So I want you to be aware of how I organize this course. This is a new way of doing it. I have not done it this way in the past. Hopefully it will help everyone out. So with that in mind, let's continue. Topics. First thing we're going to talk about, this part of shallow foundations concentrates on bearing capacity, and I explain the difference between the two, and I'll explain it again as we go along. The basic concept of spread footing design, we're going to go over an overview of that, and then we're going to have the failure mechanisms of bearing capacity, its formulation, and then how we correct for it, which is a kind of a way of diving into one of Geotech's darker little corners, is that our propensity to invent a technique which is nice in a theory and is tied with a bow, and then start playing with it for real situations. And then we have some other items we're going to talk about: local or punching shears, factors of safety. Like I said, we're not going to get an LRFD till the end of the course. Some practical aspects of bearing capacity formulations, and last but not least, we're going to touch a little bit on presumptive bearing capacities, especially for rock. Types of shallow foundations. A shallow foundation is placed within a depth D between the ground surface less than the minimum width B of the foundation. All right, look in your slides. You'll notice along here you've got B, and then this is a rectangle, so you have L, and then this depth is from the surface. That's important notation to note. You're going to be using it over and over again in shallow foundations and to a lesser extent deep foundations, so get used to it. Most shallow foundations are placed at some depth beneath the surface, and generally speaking, that depth, D, is less than the smaller dimension of the foundation, B. You remember we had B and L when we talked about elastic solutions, and I said for elastic solutions they're interchangeable, but as a general rule, discipline yourself to use B as the shorter of the two and L as the longer of the two. That discipline will definitely come in handy here. Also note that the depth is less than B, but there is a depth. All the stuff we discussed in elastic solutions and soil mechanics, for the most part, assumes that that the load is at the surface of the soil. It is the rare shallow foundation that is placed that way. Generally speaking, they are excavated. You excavate them, and you can use either a form or you can use the soil itself, depending on whether it'll hold up, to act as a form for pouring a shallow foundation. And normally you put the rebar cage at the bottom of the shallow foundation, and just with a minimum cover above the bottom. Then you pour the thing. You can pour reinforcing bars and whatnot to connect the foundation with the superstructure. You see that in the splash screen. You'll see an example of that. We have all kinds of configurations for this. Kind of a little bit redundant. We have spread footings are either finite or infinite, and I'm going to get to that in just a minute. Or either square, rectangular, or circular, which are finite, or continuous footings, which are considered quote-unquote infinite. We're going to talk about what that really means in reality in just a minute. You have ring foundations, which are basically continuous in the fact that, like a ring, they have no end, and strap footings, which are used to connect two spread footings. We also have wall footings, which are usually continuous, and you have mats or rafts, which are very large foundations, which are, even though they're not infinite, they're very large, and they have some different aspects to them from your regular spread footing. All right, footing. A finite spread footing is a shallow foundation that transmits loads and has an aspect ratio of 1 to 10 L over B. Obviously, if you get below 1, then B and L invert themselves. We're assuming that B is the smaller and L is the larger. If a foundation has a length which is 10 times or more than its B or width, it is considered for analysis purpose to be continuous and infinite. And so that is an important definition. I did mention that in soil mechanics. We'll do it again here. Once you get past that, you generally ignore the effects of the length and concentrate on the width, the B dimension. So those are continuous footings, and they're used very commonly in buildings. Particularly residential construction sees quite a few of those in this area, and you see those in many different types. It's a very handy way if you've got a wall to support. A continuous foundation is very nice, but they're analyzed a little differently from a conventional, from a finite foundation where the L over B is less than 10. One place where you see quite a few foundations which usually end up as continuous, but not always, are abutment or wing wall footings. If they're long enough, they can be continuous. If they're not, then they're analyzed as finite foundations. Basically, as you see in the photo here, you have a combination of a gravity wall, which relies on its weight to hold it in place without overturning and whatnot against the soil pressures. And you basically will be building up this area over here. You'll build that up, while at the same time, the base of that foundation right here is basically a shallow foundation, either continuous or finite. And these are very common. Like I said in the introduction, I talked about putting piles under them when the soils were not sufficient for a shallow foundation. A combined footing is either a footing with more than one load. It's usually one where you've got more than one source of load. Normally with a footing, you've got one column, say, or one wall, and it loads the footing. With a combined footing, you have more than one column. There are definitely applications for this. How this affects the design of the foundation depends entirely on how the loads are distributing between the columns and the locations of the columns. And in some cases, you'll have trapezoidal footings as well. We're not going to spend a lot of time on that. What you basically do is to resolve, one way you can deal with that is for geotechnical purposes. Now, structural is a whole different ballgame. For geotechnical purposes, if you can do it, you can resolve all of the loads into a single load. And it's entirely possible, if the footing is and the loads are all nice and concentric and everything works out, that the analysis of the footing is no different than it is with a singly loaded continuous foundation, or finite foundation as well. Mat foundations are, as I said, very large foundations. They have, most of the time, they interact with the soil. And when I say interact with the soil, and we'll talk about it in just a minute, they are flexible. They have some flexibility. You remember when we talked about elastic solutions, we had purely flexible foundation where the soil conformed itself to the soil when the soil resisted the deflection elastically, or you had rigid foundations where the foundation was perfectly flat usually, and it didn't vary, and the soil just had to adjust to that. Well, mat foundations, no foundation is purely one or the other. They are a continuum. Mat foundations tend to be, we normally assume for spread footings that they're rigid. We assume for mat foundations they're more towards the flexible end. And that's the big difference from a design standpoint between the two of them. There are other things. You don't see much bearing capacity failure with mat foundations. But it's probably better to move to the next slide to get to the bottom of why this is important. This is a little diagram which shows the difference between flexible foundations and rigid foundations in the way in which when they apply the load to the soil responds and the foundation responds. If you have typically with clays, you will have a concave type of response where the centers sag, so to speak, and the ends do not, whereas with sand you'll get the backwards. If you have an answer, this diagram assumes a uniform loading, or at least a concentric loading. With a flexible foundation, it has to be a distributed load, because flexible foundations, don't basically do very nicely with point loads. Think about it for a while. With rigid foundations, we can talk about a concentric load, and clays tend to, with rigid foundations, and I think we saw some of this with elastic solutions, particularly go back through Ferroit. You'll see that the stresses are the highest on the edges and lowest in the center, whereas with sand it's the other way around. So sands and clays respond to loading differently, and they interact with the rigidity or lack thereof of the foundation differently. However, for our purposes, we are not going to consider any of this. For the purposes of this, we're going to assume that the foundation is a simplified distribution where it's linear along the foundation. In other words, it's either uniform or linearly increases or decreases. We're not going to get into a lot of this for the application of this theory. One thing that the Soils and Foundations Reference Manual does, and I'm not going to spend a lot of time on it, is get into this sort of settlement, trying to set up a chart like you see here that relates whether bearing capacity or settlement controls. In the zone A, it's bearing capacity, shear of the soil. In zone B, it's settlement, rearrangement of the particles, elastic settlement of the soil. I'm not going to get into doing that. I will note to you that one of the things that this kind of diagram teaches us is, generally speaking, the narrower a foundation, the more important bearing capacity is. And the wider one is, and particularly getting to mat foundations, the more important settlement is. So those are the differences between the two. And that's a big difference. I'm not going to get into a formal. One of the things that this chart implies that doesn't correspond to reality is that there is a rigid line between the two. It's very fuzzy. The line between bearing capacity predominating failure and settlement predominating failure is fuzzy. Like everything else in geotech tends to be fuzzy. And So I'm not going to get into I'm not going to really go into that chart other than to note some of the things that might teach us. But, it gets fuzzier when we get into deep foundations. All right. Let's take a trip down memory lane. Plasticity, lower and upper bound solutions. I covered this in soil mechanics. Veroit has a nice treatment of this in his book. And we can learn. Basically, just to review, the common, basically the plasticity is inevitable with soils. Sooner or later, you're going to have plastic deformations or permanent deformations. Sometimes those deformations can be relatively small. In the case of bearing capacity, they tend to be relatively large and catastrophic, because what you're dealing with is shear failure. And shear failure is plastic, total shear failure is plastic failure. Not just deflects in shear, but actually, gets past the elastic limit and gets into the purely plastic zone. And as I said in soil mechanics, we're going to go into this assuming a more Coulomb's theory of failure with elastic purely plastic failure. So therefore, if you get and if you recall from slope stability, if you have a slope, and then we had circular fail surfaces in that, and we had, with circular failure surfaces, we had a situation where the failure of a slope along the surface is progressive. In other words, you start at a certain point where you start seeing plastic failure along that surface. The surface is the surface where the weight of the soil and the effects of the water and everything else that come together is basically the sort of the quickest downhill way to a failure. In other words, it's the weakest point. The soil's loading will try to find the weakest resistance failure surface in the soil. And if we begin failure, we'll start seeing plastic failure in one place. And then it will progressively enlarge if we keep loading it, if the load, or either that or the load is not stopped by some reason, or it doesn't decrease. It will progress to the point where the entire failure surface goes plastic. And when that happens, we had slope failure. We had a lot of dirt going downhill. And if you're the geotech on the job, your reputation goes downhill with the dirt. So that's very much, and so I kind of now Veroit has a more formal definition of lower and upper bound. But basically the way that I presented it in those, and in sort of a simplistic way, is lower bound takes place when at any point along that failure surface we have plastic failure. Upper bound takes place when it all fails and you have catastrophic. The use of lower and upper bound brackets those 2 points and says that the failure, that the real failure is somewhere between. We talked about, if you remember, the N factors we used in the slope charts and whatnot. Can vary, the brackets were between 2 and 4 for those, but in reality they could vary somewhere in the middle. And sometimes and that was, 2 and 4 for vertical cuts. Obviously, if you've got a slope cut, that goes down. Well, that little bit review is pretty much understands the bracketing procedure we use for lower and upper bound. Can we use this for bearing capacity? The answer is yes. We can get some ideas from about bearing capacity using this bracketing technique, and that's what we're going to get into. We went through that for slopes, but bearing capacity failure is essentially slope failure with a level surface. You don't need an unlevel surface or a sudden cut to get slope, to get failure. you need to apply a load. And we're going to talk about applying, let's start with a uniform load, and let's start on a continuous foundation. In other words, one where we don't worry about the effects of the length, just the width of the foundation. Let's look at two lower bound solutions about this. If we just applied more circle directly, then we would, and I kind of think, if Roy goes through this, and just to be real honest with you, I don't think this is a very realistic scenario. Basically what it says is that at the point where the pressure is equal to 4 times the cohesion, and we're going to assume, just like we did with lower upper bound solutions of a purely cohesive soil with purely Tresca failure, phi is equal to 0, just like your other Tresca maximum shear stress failure, just like you do with other engineering materials. A more realistic way of doing it would be to go back to theory of elasticity. And you remember this from theory of elasticity, where you use the two angles to compute the stress at any point using elastic theory. And without going through a lot of math, I'll leave the math to Roy. The pressure at which point you get failure somewhere is pi times c, pi times the cohesion, as opposed to 4 times the cohesion for the direct application of more circle case. I think that's a more realistic lower bound. I think it's a more realistic case, because basically your assumption with an elastic, purely plastic soil is that it's going to run up the elastic to the point where it hits plastic. And that's at any point where the soil stresses go plastic, so to speak, is where you get lower bound failure. And that's what you're dealing with these things. So we're going to set the lower bound at pi c. Upper bound solution. To get an upper bound solution, we would have a circular failure surface. And we're going to talk about purely cohesive soil. And we're talking about applying a pressure. And we're going to assume that it has a circular failure surface, just like we did in slope stability. And we apply that, and basically what you get here is a rotation. It rotates around that and has a nice circular failure surface. And if I take the area, length / area of that circular failure surface, now this is a continuous foundation, so length and area are both apply here. Then what I'll end up is, I do a little math, I end up with this formula over here, where the ultimate Q, which actually should be P ultimate, Roy's notation and standard notation over here a little different, is equal to some bearing capacity factor. And the bearing capacity factor is equal to 2 pi, which is based upon the length of the failure surface, times the cohesion, length / area of the surface times the cohesion. And then 2 pi is about 6.28, plus sigma naught. Now, you're sitting there looking at me saying, I don't see anywhere on this diagram where there's a sigma naught in sight. You know what? You're right. There isn't. Because Voigt's diagram here basically assumes that there's no, and remember I said just a few minutes ago that virtually every shallow foundation on the planet is dug down into the soil. And if you dig down into the soil, at the base of the foundation there's an effective stress. If the soil is uniform above that, it's equal to, and dry. If it's uniform and dry, it's equal to the unit weight of the soil times D. If it's not uniform and dry, it's a little more complicated than that. But in any event, that's what they're talking about. In other words, if you press it this way, then you'll get a resist. If there's dirt up here, you'll get a resistance that way. So I include that. I include that because I'm prepping everybody for the next step. So that gives me an upper bound of about 2 pi or 6.28. now we've established might be able to use a circular failure surface, is that the most critical surface with slope stability? You remember we had to search for that. The answer to that question here is no. If we move the center of the failure surface upward to the point where this alpha right here is 66.7 degrees, we get that surface. And if we apply a force here and the cohesion, and we do all the math, we get to the point where the failure takes place when the pressure is equal to 5.52 times the cohesion. And that is, we'll call that our upper bound. So therefore, the solution for this particular problem, assuming a lot of things, is somewhere between the n factor. Now you remember we went back to the last slide. I decided to define that by I call that n sub c. The n sub c is somewhere between 3.14 and 5.52. Now that's a fairly wide range for one thing, and that's typical with upper and lower bound solutions. You very seldom can bracket them very closely. We use that to start, so that's a good ballpark to use. There are some problems with this. The first problem, and the most significant problem, is that most shallow foundations do not have a circular failure surface and bearing capacity. Now, some do. The British geotech in Skempton came up with a method, and it's been refined and the usual dickering with it, for very soft clays. In very soft clays, you see this kind of failure. And it is used, and I've taught it in the past. I'm not going to do it this time. I'm just strictly going to use these very soft clays as sort of an illustration of how this type of upper and lower bound. So in some cases, that's a very good way to do it. However, the more common solution is Prandtl's bearing capacity solution. Prandtl is a name which is better known in aerospace and fluid mechanics than he is in soil mechanics, except for this. And he actually came up with this theory of failure using punched metals. In other words, sheet metal, punching sheet metal. And obviously you want to know when you're punching sheet metal, how much force is it going to take to induce plastic failure and punch through. And so Prandtl came up with this. Basically, he assumes a surface that looks like this. And his method was taken up by Terzaghi and others to estimate the bearing capacity of shallow foundations. And Terzaghi's theory, I think, first published in the 1940s, something like that. And of course, it appeared in his books in the 1940s. As typical, and for quite a few years, Terzaghi's formulas were used. And when I first started teaching this course, I taught them. However, Terzaghi, there have been a lot of refinements since then, and the refinements have, in typical geotech fashion, gone in several directions. We've got several Vesich, Alexander Vesich taught at Duke, Meyerhoff, who taught at the University of Halifax, and his father was Nobel Prize winner, Brinch Hansen from Denmark, all came up with little variations. I'm going to discuss what those little variations are in just a minute, towards a more accurate solution. So those are the solutions we're going to tend to in this course, rather than in traditionally a lot of courses we'll teach Terzaghi's first and then one or more of those later. We're going to just cut to the chase on it. There are some assumptions. And as I've told my students for many, many, many years, anytime something goes wrong, my fluid mechanics teacher at Texas A&M taught me this. Anytime something goes wrong, you need to, first thing you need to look at is the underlying assumptions of your analysis and see which way it went wrong. And that's true, if you don't understand the basic assumptions behind any method you use, then you're going to get into trouble because you're sooner or later going to apply it in a way in which is beyond its scope. So let's talk about this. Foundation soil interface assumptions for bearing capacity methods. Foundation is very rigid. We talked about rigid versus flexible foundations. No sliding occurs between the foundation and the soil. It's a rough foundation, and usually most construction crews will gladly oblige you with that. Loading assumption. The apply load is compressive with tension. You really cannot, these foundations do not carry tension loads, and it has some important implications. And is vertical, and it is to the centroid. There are no applied moments present. The depth of the foundation is less than or equal to its width. In other words, D is less than B. We talked about that earlier. And the foundation is a strip for infinite length. The soil beneath the foundation is a semi-infinite mass, homogeneous semi-infinite mass. There's a more Coulomb model. A general shear failure mode is the governing mode. I want to talk about that in a minute. There's no soil consolidation, and the soil above the bottom of the foundation has no shear strength. You will note, if you're looking at the slides here, or this slide, that there are asterisks. And sports fans know what that means. That means there's something funny going on. Well, the funny going on in this case is that once these nice, precise assumptions were developed, then geotech set themselves to work to try to work around them. And the workarounds both allow you to apply this theory to a wider variety of foundations, but at the same time they complicate the results. And we're going to talk about some of these. We're going to talk about these workarounds. But that's a good place to start. Those are the basic assumptions, and this is a typical way that geotech method is developed. We develop the basic theory, and then we start playing with it. Load failures are basically some assumed to be in a log spiral, like the Nautilus. And basically there are three failure zones, as I talked about earlier, for the parental bearing capacity failure. The surface is along here. Nice failure surface. You'll note that this assumes no, well, it does not assume. Actually, what it does is that it assumes the failures up to here, and then you've got this Q factor, this Q. In other words, the overburden from the base of the foundation to the surface of the soil is this Q, the effective stress, which helps to resist, as I talked about earlier, the failure of the foundation. The basic equation of bearing capacity is the so-called triple N equations. And virtually every bearing capacity equation can be cast in this form. It doesn't necessarily have all the three N's in it. Sometimes N goes to 0, you can drop them. You saw already with the circular failure surface Skempton type analysis that N sub C is the only one. In fact, that's the first one. The first one is N sub C. That's the cohesive term, and it's multiplied by some stuff. The second thing is the surcharge. That talks about the effect of the Q on the foundation resisting rotation. And last but not least, we talk about the soil weight term, the N sub gamma. And all these N factors are multiplied by some stuff. And that some stuff is defined over here. This is all in your Soils and Foundations reference manual. Make it a little easier to read. It's on the slides to make it easier to read. And so we're going to go over this we're going to go over this particular equation in detail. This is the basic form of it. We're going to talk about an expanded form for it in just a minute. All right, let's start with the n factors themselves. First, the n factor, you can, if you want to, use the equations given in the book for the n factors. That's, you know, and for n sub c and n sub q, everybody's pretty much on the same page with those. It's the n sub gamma where things get complicated. And this is where we have to make a decision or have a decision made for us. Which n sub gamma do we adopt? And that, for our purposes, we're going to adopt Vesage. And we're primarily going to do it Vesage because Vesage is the method that AASHTO recommends for analysis of shallow foundations. And that's why we're going to use the Vesage method. You see here, I've got 3 different formulations, Brinch-Hanson's and whatnot, Canadian Foundation Engineering Manual, which is what CFM stands for, and Vesage. We're going to use Vesage's formulation. I could go through, and I think some books do make you go through all 3 of them. But I think it's better just to take one step, because if you use others, Verroit, for example, uses Brinch-Hanson, which is a little more conservative than Vesage. Which you use depends upon your code environment, your experience, and so, but we're going to use Vesage AASHTO. That means that you'll note all of the n factors, all 3 of them, are based upon, are functions of only one variable, and that is the internal friction angular soil phi. That's it. Therefore, this table is comprehensive. You've got phi values running up from 0 to 45 degrees, which is a very high phi. N sub c, n sub q, n sub gamma can be read off of these. You've got them in nice small increments on the chart. I think they're 1 degree increments on the chart. So therefore, you can have, with this, read them off the chart. You can use the formulas if you want to. It just opens up the possibility of making a mistake, a math mistake, when you really don't need to make it. And we're really not smart enough, I think, to design stuff with phi of 32.7 degrees. We round it to the nearest integer and go for it. Now we have an example of this, a very simple example, and it's from your Soils and Foundations reference manual, and I have that in front of me. Basically, it is a 6-foot wide strip footing, continuous strip footing. It has a D of 5 feet, which is conveniently less than B. It has the gamma above and below the face of the foundation is 125 PCF, phi is 20 degrees, and C is equal to 500 PSF. To find the, then you're asked to find the bearing capacity. And so therefore, let's assume a general shear condition, and I'll talk about that assumption in just a minute. The n sub c values, first of all, phi governs your n values. Only phi governs your n values. Therefore, you'd look up in the table. You look over there at the table I just showed you. We'll just go back to it. Make sure it's 20 degrees phi, and 20 degrees is right down here. That's where that comes from. So therefore, you have 20 degrees. You pick the n values. In this case, n sub c is 14.8. N sub Q is equal to 6.4 and N sub gamma is 5.4, and those values, people, are dimensionless. So therefore, the Q, all you do is plug and chug, and the plugging and the chugging are shown to you in the example. The formula is identical to the one I presented you before. You just plug and chug, and you end up with an ultimate Q of 13,425 psf. Now, the second part of the problem is the effect of water. I'm going to get to that a little later when we get into the this problem is valid for the assumptions bearing capacity formulas were made for. Water is one of those things that seeps into it that challenges those assumptions. We're going to talk about the workaround we're going to do, but we'll talk about that later. But in any event, for a basic problem like this, it's that simple. You plug and you chug. That's all there is to it. Make sure that your units are consistent, particularly for U.S.-based students who are working in SI. That can be can be a little tricky sometimes. But in any event, you have the first term is simply multiplied by the cohesion times N sub C. The second term simply multiplies the D sub F times the gamma above. Notice that they use gamma A, which means that that's the gamma above. It's a unit homogeneous, no water, nothing. So that's the effective stress is 125 PCF times 5. And the last term is 1/2 times the unit weight of the soil below the foundation times its width times the N sub of gamma. And that's it. That's all there is to it. You follow it, you can get the results you need. Okay. Now that's if life were that simple, if bearing capacity is simple, and if it's stuck with the assumptions, this would be the end of it. I would say, let's declare victory and go home. Well, not yet. There's more than one type of bearing capacity. The case we're talking about is general shear, which is what the theory is based upon. The problem you run into with the reason why we have local shear and punching shear is because softer soils tend to start, with stiffer soils, we get a lot cleaner division between plastic failure. The plastic failure tends to be a lot cleaner proposition. We don't get a lot of soil shifting and all the stuff like that, and plastic failures and the line between elastic and plastic is cleaner with stiffer soils than it is with softer soils. And more importantly, the difference in settlement. There's some debate on whether we should really pursue this for softer soils. I think you will find that once you get into softer soils, that settlement will become the governing failure mode. But we have to be mindful of this. And so therefore, we have this chart, which is also in your book, that basically tells us how to, if you get into local and punching shear, and there's a lot of terms and conditions for using those reduction factors. I would use them very carefully. You need to read those and understand those. And of course, with a softer soil, analysis for settlement is, well, actually any of them is mandatory, but particularly for softer soils, it's mandatory. You talk about, they look at this chart where you have regions of general shear and local shear and punching shear and the reduction factors. You need to read those carefully when you're applying to your problems. Okay, we've reached the bearing capacity correction factors, the infamous bearing capacity correction factors. Now, I told you that we would start breaking out pretty soon from the assumptions. We've already broken out one of them. That's the general shear assumption. The other ones are for different conditions. You've got the shape correct. We have to correct factors. We have the groundwater correction factors, the embedment depth correction factors, and the those correction factors are the ones we're going to discuss. And they're basically additions, and you see the formula here gives a lot of those. And that usually, that's a fairly complicated looking formula. It makes plug and chug a little more challenging than it was before. It was pretty simple before. Now you got to think about a lot of things. I'm going to try to walk you through this to see if we can simplify some of the scary looking parts of bearing capacity factors. There are, like I said, there are shape, base, groundwater, and embedment depth correction factors. I'm going to walk you through all four of them. The first one, and the one that is probably the most important, are your shape factors. Let me caution you about something before I get started. We are doing the Ashto-Vesich system. That system doesn't only includes what incident gamma is like. It also includes different shape factors and it's corrected differently. There's more than one way to correct these problems. And as a result, you need to, now you may go out on the internet and you will find that, well, this is different. This site says this and this site says that. And, what I'm going to ask my students to do is to make, first of all, for those of you who are in the course, you need to use the shape factors put in front of you. And, just for consistency's sake. However, which theory, if you adopt a different one, or your employer or the code tells you to do something different, then you need to do that. The one thing you need to be careful of, and they're not, I'm not saying that these others are not valid. All of the, there's all kinds of different ways of doing this. The one thing you've got to be careful about in any of these correction factors is to mix and match stuff. That's not good. If you're going to do it, unless you've got a lot of experience behind you, you need to, and you know your geology, you really know what's going on. You need to just take one and stick with it, and the one you pick, make it picked for you. For example, those of you who end up working for DOTs and whatnot will probably see this. Of course, DOTs have been very slow to adopt shallow foundations to start with, but that's a whole different topic altogether. If you work for another, or if you work in a different country, different code environment, you may see different factors. So all I'm saying, particularly for my students who are taking this course directly, is that you need to stick with what's here, and so that we're all on the same page. And if you get out and somebody tells you, well, no, we don't do that way, we do it differently, well, then you need to look and see how they do it. But ultimately, you need to make sure that it's good engineering practice. But ultimately, it may not be wrong. Okay, with that little caveat out of the way, shape factors. There are two sets of shape factors in the AASHTO system. One is for shape factors when phi is equal to 0, purely cohesive soils, and the other one is for the rest of them. And they're simply a plug and chug. The shape factor that goes with the cohesion term is one thing, it's right here. The shape factor that goes with the unit weight term is the second, and the surcharge term is the last one. And these are all different. Make sure you get them straight. Make sure you don't get your wires crossed with them. So that's the first thing you need to do, is to make sure that you compute them properly, you plug and chug properly. You'll notice the biggest change that you see with these is the B over L term. The L is the big reason why we have shape factors. You also, if you look at them carefully, if L goes to infinity, then all these factors go to 1, they disappear. And that's consistent with the theory that we have. I said in the beginning that there's some continuous foundations. The shape factors will go to unity, and they will basically no longer be a factor, literally in every sense of the word, once you get past your once you get to continuous foundation. So at that, we have a point of consistency there. Those are your shape factors. The second, inclined base factors. Same division. That's important if you've got a slope in the base. Now, sloping bases are, you'll see them sometimes. There are other solutions to, and they're primarily used either depending on the stratigraphy or to create some potential for lateral loading conditions. For this course, I'm not going to be bothering you with inclined bases. So we'll just call it that. But the factors are very much applied in very much the same way as the shape factors. Groundwater correction factors. There are more than one way of doing this, and I've done it differently in the past than I'm doing it now. In the past, I have used a weighted average approach to, and I'm going to come back to this topic, but I've used a weighted average torque. With this, basically, it depends upon the water depth. If the DW is the depth of the water from the ground surface. Now, that's the first thing you ought to watch for. I can measure the water depth either from the ground surface or from the base of the foundation. This particular formulation enables me to do it. I'll take into account the fact that sometimes the groundwater level is above the base of the foundation. Now, I would be the first to admit that it's not the most fun thing to do in the world to do a shallow foundation in the wet, but occasionally it happens. Or they'll do it during the dry season when the water level's down, and then by the time the water level comes back up, the foundation's there and it's too late to stop it. So basically, if you have a depth of water 0, it basically cuts the it basically cuts everything but the cohesion, the strength due to anything but cohesion, in half. You will recall back in soil mechanics we talked about submerged unit weight. And you will recall that I said that many times the back of the envelope assumption for this is that the submerged unit weight can be guesstimated to be, in many cases, to be half of the saturated unit weight. And as a result, if that's the case, you've got a completely saturated, submerged system, then the effective stresses are cut in half. That's the governing assumption behind this thing. It does not affect the cohesion because in Moore Coulomb theory, cohesion is unaffected by effective stress and unaffected by changes in the groundwater. We'll talk about that in deep foundations, is where that really comes into play, where challenging that comes into play. But in any event, if your groundwater is at the surface, DW is 0, then you're only, so it doesn't apply to the cohesion term. It only applies to the Q and the gamma term. And you'll see they've got CW gamma and CWQ. If you have the groundwater surface at the depth of the foundation, groundwater does not affect the soil, the overburden, but it does affect what's below it, the soil weight. and how much it affects the soil weight below it, or how much it affects the bearing capacity. Because, the soil weight, basically you've got a curve surface that looks like this. There's a soil mass that's trapped in there. And the weight of that soil mass bears upon the surface, the failure surface. And if that failure surface is cohesionless, you remember that the strength of any cohesionless soil is developed by weight applied to the soil particles, which in turn induces friction. If you have groundwater interfering, it reduces, and therefore the strength of the cohesion is, in general terms, proportional to the effective stress. If you have a situation where, if you flood the thing, if you put water, saturated water all the way to the top, you reduce that effective stress, and you reduce the effective stress, and you reduce basically the ability of the foundation to resist shear. And that's basically what you're dealing with. This is a linear interpolation. You linearly interpolate. You have to decide whether you got 4 regions. The first region is the region from the surface down to the base of the foundation. Region 1. That's between dW from 0 to dt. The second region is the region between dt and 1.5 times the base, let me see, plus the depth of the foundation. In other words, the depth of the foundation plus 1.5 times the base down to this point. If the water is below that last point, it doesn't enter into the shallow foundation. It may affect the settlement. It does not affect the bearing capacity. And you must use this, and you must essentially linearly interpolate between those points. In other words, from 0 to df, and then from df to 1.5 bf divided plus df. Those 3 points. If it's below it, it doesn't matter. The water table is, as we say, very deep. So those are your groundwater tables. It's probably the simplest one I've seen to implement and the easiest one to follow, which is probably the reason why AASHTO adopted it. Embedment depth factors. Basically what this means, if you recall, we had this nice failure surface starting from the corner of the foundation. It comes down, it comes back up, and it comes back to the surface. In theory, I could extend that failure surface all the way up to the surface of the soil. In other words, it'll start here, it comes down, it goes up to the base of the foundation. If it keeps going the failure surface, I could wring a little extra bearing capacity out. That's what the embedment depth factor quantifies. And to be honest, this has been a subject of debate. The problem with the embedment depth factor is that, generally speaking, when you dig into a foundation, you put the foundation in, you backfill it. The quality of the backfilling can be dicey. They may not compact it, they may not, The best thing to do is not to include in the bearing capacity factor. So for this course, somebody might tell you to include embedment. I won't. I don't think it should be included, and there are other researchers that have not either, don't either. Load inclination factors. This is along from your FHWA book. There are a number of ways of dealing with inclined loads. In my opinion, the best way, and it's the way we do it in retaining walls, is to basically break down any inclined. In other words, an inclined load is a load that goes like this, a foundation is like this, and the load goes like this. The easiest way to deal with it is to have a vertical component this way and a horizontal component this way, just like we do in statics. Then the vertical component is analyzed like your like you would just regular bearing capacity equations, and the horizontal is basically you've got a frictional surface here, and you get the frictional forces and see if it's going to move. That's generally the way it does retaining walls. In my opinion, it's the best way. Some other have load inclination factors and whatnot, but I have, but like I said, I think the best way and the way we're going to deal with it in this course, if we deal with it, which won't be much, is to deal with, break it into two components. Allowable bearing capacity. The allowable bearing capacity, the factor of safety is very simply the ultimate over the allowable, or the allowable is the ultimate over the factor of safety. That can be computed in one or two ways. Either it can be computed, it can either be computed with a on the pressure basis of pressures. It can also be computed on the basis of force. I'm going to show you that example of that in just a second. Either way is acceptable. Okay, bearing capacity example. Shallow square foundation, 5 foot by 5 foot. Foundation depth 2 feet. Purely cohesionless soil. C is equal to 0. Unit weight is 121 PCF. Internal friction angle is 31 degrees. The load of the foundation, we're going to assume it's concentric, is 76 kips. The groundwater table is very deep. All right. Find the factor of safety against bearing capacity failure. The governing equation is the one that we presented earlier with the factors and whatnot. We're going to ignore the factors due to groundwater table, the CW factors, and the load inclination, the B factors, I just discussed that, and the depth factors. So first thing we do is compute bearing capacity factors for 31 degree friction angle. Look it up in the table. That's how we're going to do it. That's easy enough. And you get an instance C of 32.7, Q of 26, and then it's a gamma of 26. That's it. So that's easy enough. The bearing capacity example, the shape factors. Just now, let me underscore something. The governing assumption, the original assumption for this method was continuous foundations, not a square one. A square foundation does not have unity bearing capacity factors. So be careful. The shape factors, we just take the table I showed you earlier, just plug and chug. B equals to L is equal to 5. You just plug them in and do it. And you use this gamma is greater than 0 at the bottom, since gamma is greater than 0. So we use that. We plug, we chug, we get those shape factors. Other variables, C is equal to 0 via the problem statement. That means the first term is 0. Now, I used to, kind of like we did in soil classification, I used to teach this as a process of elimination process where you would eliminate certain bearing capacity, you would eliminate certain terms and then you would solve other ones. I found that students found that confusing, therefore just blindly, just insert, just like I got here, insert 0 into that. Just do it that way you won't miss anything. And then Q is equal to, which is the effective stress at the base of the foundation, is simply 2 feet times 121 PCF is 242 PSF. That's it. Gamma's 120. All I do, is plug and chug. Again, it's just a little more complicated plugging. and a little more complicated chugging, and I get 12,695 PSF. Now, that's the ultimate. Compute the ultimate load that it will withstand. Is equal to that times the area. Well, the area is 5 times 5 or 25 square feet, so I multiply 12,695 by 25 square feet, and I get 317.3 kips. Q times area. Like I said, I keep telling people that people went to geotech because a lot of this fancy math you use in stress analysis was just too much. So we keep it simple. Then you compute the factor of safety simply by dividing the ultimate by the allowable. And the allowable in this case is the design load. I want this foundation to achieve the design load. Design load is 76 kips. Therefore, the factor of safety for the design load is equal to the ultimate divided by the design load or the allowable, which is 4.17. Nice factor of safety. I can do the same thing if I use pressures. What I would do there is I would take the allowable, the QA, the allowable pressure is equal to 76,000 divided by 25 square feet. And that leaves to 34 PSF. I take 12,695, but I get the exact same result. With that, we're going to stop this particular lecture, and we're going to resume next time with the second part of the bearing capacity lectures. Thanks for watching, and God bless.